Alright kiddos, as you can tell, I am not in class today. Sadly, at this point, probably by the time your class starts, I am just about ready to meet with an orthopedic person about my foot. It's not looking good. But I still can help, well, preemptively, but help you guys with examples that we need to finish up for section 5.3. And if you guys are able to finish this movie or this video early, please feel free just to work on homework, work in groups, be good for Senor Brache. You guys got this, okay? If you have any questions, do the best you can. You have the back of the book to check the odds or calc chat. Feel free, get out your phones and bring up calc chat if that'll help, if there's time in class. Otherwise, I am hoping, I am praying I'll be back tomorrow so I can go over some questions with you. But let's try to do a few more examples. Hobbling. Okay. A few more examples to try to help you out with section 5.3, things you might get stuck on. Now remember, you have an equation and you're trying to solve. Now first thing you should see is all solutions within. Okay, so it's going to be not just one answer for inverse trig. And it's not going to be infinitely many with plus 2 pi n. It's going to be however many fit. But as we look at this equation, we're like, crud, we better use some identities. It might take you a second to figure out what identity to use, but hopefully you'll come to the conclusion that cosecant could get changed, substituted in for 1 over sine. Now as we look at this, we're like, oh, we have an addition that we can't do, but if we put in over 1, then we're going to see, hopefully, oh hey, getting a common denominator might be a really good idea in the sense of solving this equation. So then, if we multiply top and bottom by sine of x over sine of x, we can get on top 2 sine squared for the left-hand expression, all over plus 1, a common denominator of sine of x. Now we still have the equal 0 over here. Now you guys, there are different ways of going about this in the sense of maybe right back up here, maybe you would have moved the 1 over sine, subtracted to the other side. That might have also worked, but for right now, we'll just leave it the way it is. How do we solve 2 sine squared of x plus 1 over sine of x equals 0? Well, hopefully you're looking at that and you're like, wait a minute, that's division. How do I undo division? And hopefully we answer multiplication. So if we move the sine of x to the other side, the great thing about this one is that 0 times sine of x is just 0. Over here on the left, we have 2 sine squared of x plus 1 equals 0. 2 sine squared of x plus 1 equals 0. So now it's like, oh hey, alright, let's start solving. Now remember, the sine is stuck with the x. We can't undo or take away or divide by 2 sin. Hopefully the first thing you see is subtract that 1 to the other side. We've got to move that puppy. We're going to divide by 2 in order to keep solving. So we have sine squared of x equals negative 1/2. Now some of you might start looking at this and saying, uh-oh, this isn't looking good. Others of you are like, no, 1/2 is in the unit circle, no big deal. But the problem is, as we go to do plus or minus square root of the left and plus or minus square root of the right, hopefully now you see, uh-oh, is this problem even possible? Square root of a negative number? Imaginary. So therefore, wait a minute, can sine equal an imaginary number? Can sine equal, for this sake, we're just looking for real answers. Can sine be undefined? The answer is no. So therefore, for this one, I know it's weird, but the answer would be no real answers. You could also say DNE, but the answer does not exist. Or you could say this little empty set again and be like, nope, no answers, it's impossible. As it's written, it's impossible. Now let's go ahead and go check out another one I know, an impossible one. Every now and then they might throw you a weird one. Let's look at another example. This one, directions, once again, all solutions within. Okay, we're only looking for however many solutions fit between. Not just one for inverse trig, not infinitely many. Remember the first step, can you read the directions and know what kinds of answers you should be getting? Next step, we gotta look at this problem though and say, alright, solve. There's a sine and a cosine. Well, Some of you might right away start thinking about formulas, thinking about plugging in, but you're like, there are nice things to plug in for sine or cosine, and you're right. So what can we do? Well, let's move the two. You're not quite sure what to do? Oh, wait a minute. You see how they both cancel out? Now here's a weird type of example where you have to have this unit circle knowledge that, well, I've been trying to remind you guys over and over again to keep working on. Because there is not really a nice identity that will help you use this. There's not a nice plug-in in order to get rid of one of those trig functions, but if we know the unit circle really, really well, hopefully we're like, wait a minute, sine equals cosine only at a certain angle, and the only place where sine and cosine are the same, the x and y, the ordered pairs, are equivalent is at, can you answer it for me? 45 degrees. Because at 45 degrees we have root 2 over 2, root 2 over 2. Sine and cosine are the same at 45 or at pi over 4. So I know right away, remember we're looking positive pi, negative pi, we're looking for all the answers going positive pi, all the answers going negative pi. One answer we can say without doing any more math is pi over 4. All my degree ones, I know. X equals 45. Now some of you, kind of like yesterday, remember how we went to all the quadrants for that plus or minus answer? You might be like, all the 45s. But you would be wrong. Sadly, because all the 45s, the numbers match, but not the signs. So in the first quadrant, we do have positive, positive. Question, what other quadrant are the signs, or in what other quadrant are the signs the same? Second, no. Third, yes. Because we have negative, negative, the signs will be the same as we're looking at the coordinates. So then the 45 degree in the third quadrant is our other answer. Now, look at your restrictions though. Can we go there positively? 5 pi over 4? No, it's too big. So instead, we would need to go negatively in order to get that answer. So we have our pi over 4 as one answer, and then we have our negative, that'd be negative 3 pi over 4, right? Or negative 135 degrees. And then we have our answers both in degrees and radians. Alright, let's see if we can get through one, maybe two more. Let me see. Just check in. Yeah, probably just two more for right now. And I'll let you guys just work on homework. We have another example. We have another example where we need to solve all solutions within. So remember, we're just looking for the particular ones in the interval. Look at the equation. I bet we better use some sort of identity, huh? If I'm looking at it, I'm looking at this thing. 1 over cosine for secant. Sine over cosine for tangent. That sounds pretty good. Because with 1 over cosine, sine over cosine as a common denominator, we use the reciprocal property and then the quotient property. We can put those together and have 1 plus sine of x all over cosine of x equaling 1. Hopefully from that last example you guys see this and say, wait, division, ew, who likes that? So let's multiply the cosine to the other side. Times cosine. Feel free if I'm ever going too fast, because I'm just kind of going by myself here. Have seen or watch a positive video, and then you can catch up a little bit if you need to. But now we have our 1 plus sine of x equals cosine of x. Now this is a little hard. This is also a unit circle knowledge. We could try going and finding some weird properties in order to try to help us, like maybe cosine is sine of pi over 2 minus x, the co-function property, but that just doesn't sound fun. If we think about the unit circle, and we think about this 1 right here, we think about all the different values that sine could be and cosine could be. Remember, cosine has to be in between 1 to negative 1. It can't be any bigger than 1, can't be any lower than negative 1. This sine also, same dealio, has that restricted range in between negative 1 and 1. if you think, if we're adding any positive sign values to 1 plus a half, that'd be too big for the cosine restriction. 1 plus root 2 over 2, 1 plus root 3 over 2. All of those would be too big for their restriction. So sine actually can't be any positive value. If we go negative, 1 plus negative 1 half, 1 plus negative root 2 over 2, 1 plus negative root 3 over 2. We are going to get some funny values, but actually, the only one I can see that would match up the unit circle would be 1 plus negative a half. But if sine was 1 half, cosine won't be 1 half, so that's not going to work. However, if we were to think about what if sine was 0? Well, it's a weird one. We're thinking kind of outside the box, trying to work with our unit circle values. If sine was 0, what would cosine be? 1. Because we're talking about the value squared. Sine is 0, cosine is 1. We also have, that's at 0 or 2 pi. We also have at pi, 0 and negative 1. Well, which one of these actually fits with the equation that we have? Look at it. If sine is 0, 1 plus 0 is 1, that only works at 0 or 2 pi. We're looking once again only to positive pi, only to negative pi, the only possible solution would then be 0. As you guys notice in this example, some of these aren't super easy or nice to solve. Not that any of them are easy, but some of them don't match up with the unit circle well. So the very last example we're going to cover, and then you guys get to work on homework, is using your graphing calculator to approximate solutions. Now remember, I'm going to do it in radian mode just because the answers are simpler, they're shorter, but they're going to be nasty decimals. So that's why we're saying approximate. We're not going to have pi's in there, we're not going to have exact answers in there. So I already have this equation in my calculator. If you look at this equation, equal to 0, if we're trying to use our graph and solve, then we're going to find the zeros in our calculator. Now, the struggle is if you look at the directions, it really doesn't give you much as far as where to be looking, so that was my bad. I wasn't specific enough. So we'll say for x within 0 to 2 pi. Looking for all the answers in between. So now if we go to our graphing calculator, I'm trying to use my crutch. Oh, no. There we go. If we go to our graphing calculator, I already have the equation put in. I'm in radian mode. Because the answers are smaller. We could go ahead and do that zoom trig. Remember, it's number 7. However, if you do zoom trig, we're like, wait a minute, what angles are we looking at? We're only supposed to be looking between 0 and 2 pi. So then we could change our window. Just to look at 0 to 2 pi. Remember, we can type in our x-min and x-max. There we go. So now we're only looking at where we're supposed to be looking. How many intersections do you see? Count them off. 1, 2, 3, 4. I got a calculus kid go turn on a light. You always turn on. I see 4 different intersections with the axis, but remember, we're not doing intersections in this problem. They're just zeros, no big dealio. So we'll go ahead and do second trigs. We can find our zeros with the number 2. Kiddos, for sake of time and stamina, I'm just going to find one of them. You guys are amazing. I trust you to find the rest.
What's wrong? How are you going to teach us?
Pour a shower is distressed. Okay, so we have one intersection of 2.356195. You guys are awesome. You can do the rest as you do. There's a D. 1, 2, 3, 4. Yes. All right, HonorsPrecalc kids, thanks for paying attention. You guys get some time to work on homework. If you need to pull it up, somebody has a phone. You know, you get into your shared folder and you can find it and share with the rest. Maybe put it in the front board to help them out, help Senior Roshi out. Hoping, praying, you guys be praying too. I'll be back tomorrow. Talk to you guys later. Bye.